When a conductor is placed in an electric field, then the field line can actually emit out of the conductor. However, all the field line might passes out of the conductor, while few of them might pass out of the conductor. But if we are interested in determining the magnitude of the field line that passes through this conductor, then we need to discuss about electric flux. The electric flux is the net electric field that passes through a surface, where the surface is a metallic conductor. The symbol we use to denote electric flux is this, where most textbooks can refer it to be phi. So regardless, the goal is to understand the basic idea behind it. To determine this electric flux, 3 formulas has to be put into account. These formulas will depend on the nature of the surface in contact with the electric field. So what am I saying makes sense? The first scenario, when the electric field line, when it is parallel or perpendicular, let's say perpendicular to the surface in contact. So let's say this is the surface. So the field line is perpendicular to it. Now it's obvious that a normal to this surface is parallel to the field line. A normal has to be perpendicular to the surface. So either you extend it to the left or you extend it to the right. Regardless, it will be parallel to these field lines. Now, when 2 lines are parallel, geometrically, what is the angle between them? 0. Excellent. The standard formula to find the magnitude of electric flux is equal to the product of the electric field line, the area of the surface in contact, multiplied by the cosine of angle theta, where theta is the angle between the normal line to the surface and the field line itself. Now, for the first scenario we said we put into consideration, we said the angle between the field line and the normal line to the surface is 0. So tell me, what is the cosine of 0? 1, right? Excellent. So it means when the surface is perpendicular to the field line, then to find the magnitude of the electric flux, just multiply the electric field and the area of that surface. 7. Am I communicating? Excellent. So let's consider the second case. Oops, I have to. Perfect. To save space, that's why I have to do that. Good. Now the second case is when that surface actually makes an angle with the field line. So what are we saying makes sense? Let's put that in green. So let's say we have this, we have this, we have this. Now the surface is now at an angle to the field line. So the field line emerges out. To have this, to have this, and to have this. Perfect. Now what do you observe from this structure, from this diagram? Notice that if we are willing to draw a normal to the surface, then if this is the center of the surface, for instance, then a normal to the surface has to be perpendicular to the surface, so it has to be moved in this direction. As you can see, as this normal is going, it's making angle with the field line. So the angle between the field line and the normal to the surface, when you observe that the surface is not parallel, neither is it perpendicular, then in this case you have to put it into consideration. So for this kind of situation, then the electric flux I or phi is equal to EA cosine theta. The value of theta has to be put, is a very crucial thing you have to put into account. Am I communicating? Perfect. So this is the second scenario. Now for the third scenario, this is a situation whereby the surface is parallel to the field line. So let that be in red. So here is a field line, and this is the surface. So what do you think? If we draw a normal to the surface, then what do you think will it make with the field line? Well, That will be 90 because it is perpendicular to the feed lines. However, the cosine of 90 is indeed 0. So this clearly tells us that for a feed line that is parallel to the surface in contact, then there will be no net electric field that will be emerging out of that surface. And that makes sense. As you can clearly see, the surface is parallel to the feed line. No feed line is actually going into it. So where would feed line actually come from to emerge? Except if there's still an inbuilt feed in that object, because the object might be carrying some other charge. The charge has to produce its own feed line as well. Otherwise, there will be no feed line that will emerge out of the surface. So it means the relative flux will be 0, because cosine 90 is 0, and we multiply 0 with EA. Now it gives us 0. Am I communicating? Now this concept will actually make us to make a very important conclusion, which include when the electric flux is going to be maximum and when it's going to be minimum. Now pause the video and decide yourself, and after that you can unpause it and see if you actually make the right decision. Well, for the maximum, the electric flux will be maximum when the surface is perpendicular to the feed line, which is this. This will be the highest value we can have. This one will be affected by the value of theta. However, this one is nothing. Am I communicating? So this one has no effect. You multiply the magnitude and the area, you get your answer. Am I communicating? Perfect. Now, this might be in other words. Instead of, if it is a multiple choice question now, we said, okay, it's maximum when the surface is perpendicular to the feed line. However, it can also be in relation to the normal to the surface. So how will it come that way? The electric flux is maximum if the angle between the normal to the surface and the feed line is 0, or if the normal to the surface and the feed line is parallel. You can rewind the video and listen to it over and over again to get the concept. Perfect. Now, for the minimum, this is maximum and this is minimum. So when is it said to be minimum? It is said to be minimum when the surface is parallel to the feed line. Simple as that. Or when the normal to the surface is at the right angle to the feed line. Or when the normal to the surface is perpendicular to the feed line. So that's how questions can come. So I hope this gives you a clear insight of what electric flux is. It makes sense. However, while dealing with problems involving electric flux, please you have to make sure that the sign associated with the charge is put into consideration. That's what tells us the sign that will be attached to the flux. As a consider example, you will see what I'm saying makes sense. I hope you got that. In order to make use of what we have discussed and learned into good use, let's consider some examples. Example number 1. A spherical surface of a radius 0.5 meter encloses a charge of positive 2 millicoulombs. What is the electric flux through the surface? Let's write out what we know. R radius is given as 0.5 meter. And the magnitude of the charge Q is positive 2 millicoulombs. Unfortunately, not in the appropriate units. So milli to coulomb, you multiply with 10 to the power of negative 3. So we have plus 2 times 10 to the power of minus 3 coulombs. Excellent. Now, you will observe this problem doesn't in any way tells us if the spherical surface is perpendicular or parallel, or if it's at an angle to the surface. However, for them to ask us to find the electric flux, it means it is not 0. And before we can use that second formula, we must have the value of theta. However, remember the first formula, we really don't need the value of any angle to get there. So we are using the first one. Am I communicating? So not all problem will be specific. Some problem might want to just know if you know what they are doing. Am I communicating? Perfect. So therefore, we are using the flux phi to equal to EA. Another problem, the magnitude of the electric field is not given, just the charge. But remember, for motor length in electric field, E is KQ over R squared. Also, for sphere, how do you determine its area? The area of a sphere, which I can represent as S sub x, is 4 pi r squared. The volume is divided by 3 and cube the radius. And for the hemisphere, you divide by 2 pi r squared, 2 over 3 pi r cube. So it depends, whichever you are dealing with. So instead of E, let's replace with this. And instead of A, let's have this fixed in. So therefore, we have KQ divided by r squared multiplied by 4 pi r squared. Now the r squared can leave for now. And then left over is KQ. But I said 4KQ, that makes sense? 4KQ pi. Perfect. Now K is a Coulomb's constant. However, it can be simplified to 1 over 4 pi permittivity of free space, epsilon naught. So it can always help us to simplify this expression more forward. So let's replace it with what it is. So we now have 4 times 1 over 4 pi epsilon sub naught times pi again. Now the 4 can leave. Pi can also go. Then we still have times q. And finally, we can have q by epsilon sub naught. So this is another formula that can help us to determine the electric flux. Now this is enough for us to get our final answer. So that will be 2 times 10 to the power of negative 3. Put it in positive, divided by, what is epsilon sub naught? You should remember, 8.85 times 10 to the power of negative 12. So let's type that into our calculator and have our final answer. So I got 2.26 approximately times 10 to the power of 8. So the unit is Newton meter squared per coulomb. Perfect. So that's our solution to this example number 1. On to example number 2. Find the electric flux through a squared surface with side length of 2.0 meter if the electric field is constant and equal to 2000 Newton per coulomb. Assume the surface is at an angle of 60 degrees with respect to the field line. So the question asks us to find the electric flux. So which formula are we using? As you can see, this question is actually discussing about angle. So we are using electric flux phi equals to EA cosine of theta. But tell me, is this 60 degree, is it the angle we are going to use? What do you think? Pause the question video and answer it. Then after that, you're going to pause and see if you got it right. Assume the surface is at an angle of 60 degrees with respect to the field line. Remember, you have to use angle that is between the normal to the surface and the field line. But this one, it is the surface itself and the field line. Now, when this occur or take place, you see the angle between the surface and the field line and the angle between the normal to the surface and the field line are complementary. So if you are given the angle between the surface and the field line, you just need to subtract that angle from 90 to get your actual angle, which will be the angle between the normal to the surface and the field line. Am I communicating? Perfect. So therefore, the actual angle we'll be using will be 90 minus 60, not 60, which will be 30 degrees. Assuming the question come in this manner, that assume the normal to the surface is at an angle of 60 degrees with respect to the field line. Absolutely, that makes sense. We can proceed on using 60 like that. But with that being said, we have to do the normal process. It means I is equal to, the magnitude of the electric flux is 2000. Now, the surface is a square. Area of a square is L squared, remember. That's 2 squared. Then multiply by the cosine of 30. So I'm using my calculator for that, straightforward, and get my final answer. So I'm typing 2000 times 2 squared is 4 times 4 times cosine of 30. Okay, I got 6,928. Remember, Newton meter squared per coulomb. So that's our answer to this problem as well. But now you should have been getting used to the logic. that's how you can easily solve problems involving electric flux. I hope you find this video helpful and understandable. Thanks for watching. See you in the next video. Bye for now.